Optimize. A journey through database carry optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
So this last lecture before the break. So today we're going to continue the discussion of how to use the cost models inside of query optimizer to estimate the now is going to be how much data we think an operator is going to emit, because again, that's going to be the backbone for how we do cost model calculations. For you guys in the class, all right, project one is obviously due this February 28th. Who here is not finished? I haven't looked at the Greek yet this morning. Sort of. Okay. I mean, somebody asked for an extension. I mean, I can give you one, but it's like, if we say Sunday, is that enough? Who hasn't finished? He's nodding yes. Okay, let's just say Sunday, whatever that is, March 2nd. Yeah, it's March 2nd. Sorry, let's make it due Sunday, March 2nd. Not a big deal. Again, it's a special topics class. It's more about the journey rather than the outcome. And then project two is the proposal for you guys will be due first Monday, March 10th when we come back from spring break. I sent emails out to some of you for the assignments, and then the spreadsheet updated with the green. The green indicate it's been approved. I will send up follow-up emails to every group tonight, with additional materials and what you need to get started on some of these things. Right, there's some additional papers I want to throw at you guys to take a look at, and how to sort of get started on certain things. And then I'll be in my office hours today, and then I'll also be around excuse me, next week if you want to meet either Zoom or in person. Is anybody going somewhere exciting for spring break? That doesn't count.
It's exciting.
Yeah, it's not. I agree with him. Like Silicon Valley or San Francisco?
No, like San Jose.
All right, it's even worse. All right. All right. How does it? One year, one kid didn't do the project in this class because he went to Miami for spring break, and then had to come back and had to fail him. So I'm not saying I'm doing that. Just like if you can go somewhere exciting, do that. Okay. All right. So again, last class was all about the data structures that the data system is going to maintain inside its catalog that are going to be approximations or summarizations about what it thinks is inside of the tables. Right. Again, in some cases, like for data lakes, you may not actually have any statistics. We didn't talk about like what Parquet files maintain inside of them, but it's not much. It's basically zone maps, some Bloom filters, but there's not really good statistics we could use. So there's not anything like histograms here. And so again, these are data structures we're going to maintain that are going to summarize what's in the tables. And the most common data structures people are going to use are going to be a combination of equidepth and n-biased histograms or heavy hitters, right? And we saw in the case of Postgres, they had the histogram was just an array of values and an array of frequencies, and it stored that as a regular tuple. And then for heavy hitters, again, it was just a list. And then in some cases, hyperlog is being more widely used today because that gives you a pretty cheap and easy way to estimate the number of or the distinct cardinality of a set. So again, today's class is really how to take these things and then compute the cardinality estimate, or compute how many tuples you think is an operator is going to produce or emit, either with a single predicate or across all the predicates within a single operator. Because again, that's going to be the backbone for how we determine the cost of an operator, right? And remember we said that the cardinality estimate is going to be a logical cost that regardless of what join algorithm you're using or what filter algorithm you're using, or even what order you apply the predicates, the cardinality is going to be always the same. And then we can then extrapolate from that what is going to be the physical cost. All right, so I sort of already said this, but cardinality estimation is, again, how the optimizer is going to be able to predict the number of rows that expects an operator, should be operator, not operation. An operator is going to generate, right? Like a scan or a join or a filter. And then, again, this is the backbone for how we're going to be able to determine whether one query plan is going to be better than another. And at a high level, the way this is going to work is you just say, oh, I know whatever it is, the predicate I may be applying and whatever operation I'm doing. Like if it's a scan, you have a filter. If it's a join, you have a join clause, right? And on that predicate, you have this notion of selectivity. Like what's the the probability that any tuple from your input is going to be admitted as part of your output. You take that selectivity estimate, you multiply the number of tuples that are coming into you, and that gives you roughly, or gives you an approximation of what you think the cardinality is going to be. Right? So today we're going to talk about the basics of how to do cardinality estimation, and then we'll talk about the survey paper you guys read from the Germans, which I think is phenomenal. As he said, it's a well-written paper. And then I want to finish up just talking about so what Postgres does and SQL Server does, because you definitely see two. I mean, in the results from the paper, you definitely see like how the quality of SQL Server's cardinality estimations are superior to Postgres, and that's going to lead it to getting better query plans that are closer to what the actual true cardinality estimates are going to be. So to do cardinality estimation, there's 3 core operators we need to be able to support, right? Selection conditions like filters, join size estimation, and then distinct value estimation, right? And if you have these, especially the first one and the second one, then from there you can build upon those and handle all the other operators that your data system might support, like do multi-way joins or multiple table joins, group bys, aggregations, and so forth. Right, so a lot of the research, a lot of the focus has been on how to handle these 3 things, because again, these are then allow you to do the more complex things, and you're sort of building up from these basic calculations, these basic constructs, right? All right, so this should somewhat be redundant from the intro class, but I forget whether we actually cover this anymore. I don't think we do all of this, but the basic idea is that we can derive statistics from we can derive the cardinality estimations and statistics from the statistical models that we've computed or calculated, the histograms and other sketches from our tables, and then we can use that to sort of plug and chug some formulas that are going to allow us to produce the cardinality estimations. And a lot of these techniques I'm going to show you today, like these go back to System R from the 1970s. I think even the System R paper talks about some of these basic formulas, and we didn't go over them in much detail, right? So the basic idea is like you have a way to predict the number of tuples in R, and then you have some function v that's going to tell you the number of distinct values for an attribute in that given table. And again, this is where a hyperlog log will help you, because if you have this per table, per attribute, you can get this information. And then from this, you can now generate what's called the selection cardinality, defined by this function sc. And this is just going to be the average number of records you expect to get with a given value for an attribute A, divided by the total number of tuples you're going to get, right? So it's sort of again it's the taking of all the tuples that I'm going to get, all the tuples that are coming into me as part of my input for an operator, how many tuples do I expect it to produce as an output? Like they're going to qualify on some attribute or some predicate. So from this, you can then compute what's called the selectivity on a predicate. And the easiest predicate you can handle is an equal clause, right? And obviously, there's some optimizations you can do if you know that you're doing a quality predicate on the primary key, but we can ignore that for now. Right? So say you have some query here, select star from people where age equals 9. Right? So you're trying to find a bunch of 9 years old. So for this, the formula is really simple, because it's just the selectivity is computed from the number of occurrences we have from our histogram for the values we're trying to do a lookup on, divided by the number of elements or number of tuples in our input, right? So in this case here, to do the selectivity on age 9, you just jump in the histogram, find this entry here, right? And it says 4. So therefore, we know the selectivity is going to be 4 divided by 45. So you can have 45 tuples if you add up all the histogram counts here, right? And so the selectivity of this predicate, age equals 9, is 0.08. Of course, the last class, what did I say? I said nobody actually stores the full histogram like this, because for every single value I may have in my attribute, I don't have to store an exact count, because that'd be terrible if I have like a monotonically increasing value, where I'm just storing all the values over again with a count of 1, right? So now we have to adapt these formulas to handle the when we have an equideth histogram. So in this case here, we take age equals 9. We find out what bucket we belong to, right, in here. And so we know we have 9 elements. The total count of this bucket is 9. and this one has 5, right? 9, 10, 11, 12, 13, 14, 15, or 9, 10, 11, 12, 13, 5 distinct keys. So you take 9, divide it by 5, and then divide that by 45, and then you get an approximation of a selectivity of 0.04. So the first number here, this is an exact value, right? 0.88. Because again, I had a histogram that told me exactly the number of tuples I had for age equals 9. But now because I'm combining or aggregating together the counts for the different keys within a bucket together, I need a way to approximate how many keys I think, or how many instances I'm going to have for a given key within this bucket range, right? So this brings up one of the first approximations that we're going to have to make in our query optimizer. And again, this is not going to be, this is pretty much how everyone does this. We'll see SQL Server tweak this a little bit at the end. But they're going to make this big assumption that within a given bucket in our equidepth histogram, the distribution of the values or the keys are going to be uniform. Meaning, again, going back here, I don't know how many exactly number of keys I have, or number of instances I have for key 9, or age equals 9, but I know I have 5 other keys in the same bucket. So I don't know what that distribution is for inside of my bucket. So I just divide it up evenly, and I assume that every key would have the equal number of occurrences, right? So by doing this, this simplifies just how we can do our calculations, because otherwise we'd have to maintain additional information to have a more exact estimation of what the actual true cardinality, or sorry, true selectivity of that predicate would be. So this assumption is super important, and there will be 3 other assumptions we're going to make. Again, basically it's going to allow us to simplify the problem so we actually can compute something rather than nothing. But in some cases, these assumptions are going to be incorrect. But like, it's the best you can sort of do right now without having exact data. Sampling could solve this problem, and in some cases, if you have a good sample, it does. But again, like it's impossible to have a complete sample. Right? There's no guarantee that you're going to have a full representation of what the real data looks like. All right, so next we got to deal with how to do range predicates. So here we now have select star from people where age is greater than equal to 7. So the basic formula for this, again, assuming we have equidepth histogram, is that we know we have a starting point for our range, right? Where we're going to start at 7, and we want all the occurrences or all the keys that are greater than equal to 7. So you first start up with the range rows where we're above the bucket where we know our starting point is. So we know 7 is going to be in here, going from between 6 to 8. So in this case here, for all of for the buckets to the right of me, then I want to include them, right? So I know I'm going to have 9 plus 12 occurrences because the 2 buckets are 9 plus 12. And then now for the key for the bucket where my key lands in, 7, again, I have to make that same assumption about uniformity that I did before, where I don't know whether how often 7 and 8 occur within my bucket relative to 6. So I'm just going to divide the count here by the number of keys. That's 12 divided by 3. And then I know I have 2 keys inside this that would match. And therefore, I multiply the count by 2. And then divide that by 45, because again, I have 45 keys throughout my entire histogram. And then I produce my estimate like this, so 0.6. What's the big assumption we're also making here? In addition to uniformity, what's another one? I mean, so in this case here, again, my histogram is based on the age column. So I know I'm basically going to have a continuous set of values. Right? There isn't all of a sudden like a bunch of 7 and 8-year-olds all died, right? And there's nobody left, in this range. I know there's going to be somebody within this range. But again, not all attributes, not all value domains are going to be like that. So I may have gaps. And if I'm doing a range predicate like this, I don't actually know whether a key actually would even exist, because I'm not going to store all the exact values within a bucket. Right? My toy example here, because I had to fit it in PowerPoint, it's pretty easy to see, oh yeah, 6, 7, 8. But again, think of like larger ranges, maybe like 10,000 keys, because that's sort of how things got chunked up. I may have gaps in that. And then so I now may be counting or including the additional counts for keys that don't actually even exist. In this case here, I would end up overestimating the selectivity. So this is assuming that we have a continuous distribution of all the values within a bucket, but there's no guarantee for that. Again, sometimes you can know that, like, oh yeah, it's likely to be there, like if it's an auto increment key. But again, in that case, you don't want, maybe don't, well, you still maintain equidistant histograms, but someone could still delete keys within that, the auto increment range, and you would have gaps. But the formula would still work. Again, you just be overestimating the selectivity. All right, negation is pretty easy. Negation is just the inverse of an equality predicate, right? So in this case here, age doesn't equal 2. Well, that's simple. Well, first I'm going to just compute what's the selectivity of age equals 2, right? Because it's an equality predicate. I jump here. I do the same formula that we did before, right? I have 5 keys inside the bucket. Take 12 divided by 5, divide that by 45, and then again I just take subtract that by 1, subtract it to 1, and then I end up with the estimate of 0.95, right? That's pretty straightforward. Negation isn't that common, but it does show up, and you definitely still need this. So you can kind of see now what's happening is that these selectivity estimates that we're making, they're basically probabilities, right? It's like, what's the probability that a tuple within some input is going to match my predicate, right? And so because now we sort of think of it as a probability, you can do all the tricks you did in Stats 101 to combine them together to start doing more complex things when you want to start handle multiple predicates on the same table at the same time and want to start computing them, right? So again, we know how to compute things for a single predicate, but now the question is can we actually combine them, right? So again, the challenge is that even though the attributes, like in these two predicates here, they're on the same table, but the value domains, their distributions are completely different, potentially independent of each other. Not always the case, and Microsoft argues the opposite. We'll see that in a second, but there's nothing you can learn from age equals 2 that helps you to filter things out from the name clause here, right? Again, in practice, this is not always true. If you do know that they're actually correlated, remember last class we showed how to create correlated statistics. I can tell the data system, hey, create a histogram for these two columns together instead of doing them one by one, because I know they're correlated, and I'll be querying them together all the time. All right, so in this case here, I can compute the selectivity for age equals 2 and name like A followed by a wildcard. I'll point out also too, for substring matching, you can't use histograms for this, right? Because again, there's gaps and things like that. You don't want any false negatives. And so in some systems, they'll actually maintain separate data structures like a trie or something, or use the sample mechanism we talked about, or method last time, because that allows you to actually then compute the estimates correctly on strings. But we'll ignore that now. All right, so essentially what we're trying to do, you can think of like we have two predicates, P1 and P2, right, mapping down from here. And this sort of circle is all the things that are going to match predicate 1. And this circle is all the things that are going to match predicate 2. So what we're trying to figure out is what is this overlapping range in the middle here, the intersection, right? Because that's going to give us what the selectivity of these predicates put together. So to make this work, most systems are going to do another assumption called the independent. We assume that the predicates are independent. And the basic idea here is that as I said, the selectivity of one predicate is not affected by whatever values are being selected by that first predicate for another predicate. So therefore, if you assume they're independent, what do you do in Stats 101? You can multiply them together, and that'll give you what is perceived as the true selectivity of the combination of the two predicates, at least when you're doing a conjunction. All right, so going back to our example here, right, we're trying to figure out what this middle part is. So if we just assume that we have two predicates and we're combining them with the and, we take whatever selectivity of the first predicate, multiply the selectivity of the second predicate, and that produces our answer, right? And then it's just plug and chug to end up with a selectivity like that. Do we think that's a good idea or a bad idea? It's bad. I mean, I've already given the answer, because if it's correlated, then this is going to be way off. And we'll see an example in a second. But again, what's the alternative? What can you do? Microsoft Microsoft is basically going to do the same thing, but they're going to diminish or reduce the weight of additional selectivities when you start multiplying them together. And we'll see at the end of class today. All right, so that's conjunctions. Disjunctions is just the inverse, right? Where you take the selectivity of the inter two predicates, and then you're going to subtract it from the multiplication of the two predicates together, right? So you're basically trying to figure out what is this entire range here, right? So again, plugging, chugging with the example, you just end up with a formula like this. And again, for this, they're assuming that things are independent. In some cases, if you're lucky, you can rewrite the query to get rid of the or clause. Not always, right? It depends on what the predicate actually is and how it's being used with other predicates. Sometimes there's redundancies in the predicates with disjunctions, and you can rewrite those out. But it's not always the case you can do that. And this would be something, this rewriting phase would be done, again, in sort of like that normalization step or the rewriting step before you maybe do the cost-based search. You would recognize that I can rewrite disjunctions in a way that's better for me later on. All right, so let's go see why this independent clause is going to cause problems for us. So this is a really great example from Guy Lohmann, the guy that built the Starburst project paper we read earlier. Right, so consider a really simple database that contains cars, right? And then we have 10 makes and 100 different models. Right? Make would be like Honda, Kia, Toyota, Ford, whatever, and then the models would be like the Camry, Accord. Pick your favorite car, right? So now a query shows up with a predicate like this, where make equals Honda and model equals Accord. So if now we assume that independence clause and uniformity assumptions from before, when we compute the selectivity of this where clause here, we would take the first part would be on makes. So we're looking for one key because it's a quality predicate. I have 10 car manufacturers, 10 makes. So that's 1 divided by 10. And I'm looking for one model, the Accord. So again, I have 100 models. So it's 1 divided by 100. So I multiply those two again together, which I'm assuming I can because they're independent. Then I get a selectivity of 0.001. But we as humans know that these aren't independent because what other car manufacturer makes an Accord, right? There's only one. So there's a one-to-one correspondence between the model and the make. Again, they're correlated. Similar things like if I know that the city you're in, I know what zip code you're in. Those are correlated. So the true cardinality should just be the 1 over 100, which gives us 0.01. So we're off by order of magnitude in our cardinality estimation for a really simple query because of this correlation here. So this is just a toy example that shows you like, yes, these assumptions are going to make things easier for you in implementation, but it's going to have some pretty dramatic problems or consequences when you start running your query optimizer because the cardinality estimates are going to be way off. And again, and then the paper you have from the Germans, it talks about, oh, well, if you're uniformly always off, does that always cause problems? Or sorry, if you're always wrong and you're just wrong the same amount always, does that make a difference? Well, they show basically you're not always wrong by the same amount. That some queries, the difference between where you start and what the actual true cardinality is and what the estimate is can be quite significant, and then that causes you to end up choosing bad query plans. So any questions about this? Yes?
How do you fix it?
Question is, how do you fix this? Which one? The uniformity or the independence one is a tough one. So again, I don't know whether there's any experiments that show the Microsoft one is the right way to do it, but like the textbook talks about this, and then I think it's in their documentation where again it's when you still multiply them together as if they're independent, but you rank them and you sort them based on their selectivity. Let me jump ahead. I'll show you what I'm talking about. I don't know why I can't use the mouse. Sorry. Let me just jump ahead, and I'll come back to this later. So it's this bottom here, right? So they're going to use this exponential backoff, where they're still going to multiply the predicate selectivities together, right? but they're first going to sort them by which ones are the most selective, like from S1 to Sn. And then for the second most selective one, you're going to take the square root of it, because it diminishes the effect of it, right? So instead of the problem is you don't want to underestimate, right? So if you reduce these values when you multiply them together, that reduces the underestimation cost.
That's a hack.
He says it's a hack. Do you understand what's going on, right? So again, like you take whatever the predicate you estimate to be the most selective, right? Just doing the formulas we talked about before, right? Let's ignore joins. Like assume it's in a single filter. All right, and then so you rank them, you sort them based on what their selectivity estimate's going to be. So then you take the first one, take its full selectivity, right? Just leave it by itself, and then when you multiply all the other ones, you exponentially reduce their effect on the end selectivity estimate, so that the least selective ones don't have a large effect. Because the idea is that you're going to run the most selective first, so you want that one to be the most pronounced in your selectivity estimation.
You're sort of assuming correlation for every single, because you're assuming correlation.
Yeah, so you're assuming correlation, right? So Microsoft says that they found in their real workloads that the selectivities aren't independent; they're actually positively correlated.
Always.
They're not assuming everything's 100% correlated. They're basically like saying it's better to be partly wrong all the time than it is to sometimes be really, really wrong.
So the goal is to put an upper bound how wrong you are.
Like this is still not solving the problem. It's just
Yes.
changing
This is really not solving.
I mean, it's
Wouldn't a better idea be to maintain a multiplier for your estimation?
the question is, his statement is, would it be better to basically figure out what the weight of these things should be?
Yes.
And then you have to
Or
then you have to look at the data and actually there'd be a lot. It would increase the complexity of your statistics. You have to actually run all these.
But doesn't the survey people kind of argue that you need to increase the complexity of your statistics, and that's like the main thing holding for your
Everybody, yeah. So his statement is, in the paper you guys read, everybody's underestimating,
Yes.
right? Again, and that would happen if you without these square roots, then this thing is going to become way more selective. So right, so therefore you're underestimating number two is going to come out. So by reducing this, by having this reduce the weight of them,
Right.
then you get closer. You're moving back up to that middle line.
Right. But this is like a greedy approach to a problem that requires DP, right? Like it's like you're solving this problem.
All right.
Like to solve the problem, you actually have perfectly. You would have to calculate the correlation for every single variable in each table.
And there is
You're
no,
gonna be looking
and there's
calculating
nothing like
every
that.
single piece
No,
of
and
data.
then if you do that, then you already have the answer to all those things.
Like that's
No, but when you're running analyze, you could just run those.
But so a couple things. One, you assuming you know what the predicates are going to be ahead of time. Now, there's an Amazon paper we're not reading in this class where they talk about like 90% of the queries or 99% of the queries show up look exactly the same. Like not even parameterized, the exact same parameters from day to day. So therefore, you could compute that things. But of course, now if data evolves over time, then whatever those estimates could change. But like, I don't think I don't think it's going to change dramatically from day to day. But I think it's something you could learn. All right, so I realize this is not exciting for me reading from the book, but so Microsoft SQL Server made a major update to its cardinality estimator in 2014, based on the aggregated benefit observed for over several OLTP and data warehousing workloads. In practice, it made two changes to the assumptions. First, instead of assuming independence, it assumes that data distributions on different columns are positively correlated. However, instead of assuming perfect correlation, it also assumes a so-called exponential backoff. That's this, where you're increasing the number of square roots you're doing. Model correlation, which strikes a middle ground while still keeping the overheads of statistics low. Again, the overhead of actually computing this is trivial. Whereas like if I had to maintain or learn something what the weight actually should be, right? So let's just say like Microsoft's not dumb, right? The SQL Server optimizer team, that's like cream of the crop. Like Cesar, Nico, and Surgeon, all those guys, right? I don't think it's not like they're like sitting around at lunch. Hey guys, what if we did this? Yeah, whatever, put it in. Like, push that commit, right? Like they sat and like looked at the traces and tried to figure out whether this actually makes sense. Nobody else does this as far as I know. Again, the textbook talks about it. The sequence order documentation talks about it. But as far as I know, nobody else actually implements this. So, yes.
Are there any systems that will like do different optimization if you're doing like a repair statement than like just running statement? Like for this, like you can calculate a lot. If you're say, okay, if I know you're suggesting to me I'm going to prepare a statement, then you're suggesting to me, you're hinting I might use this multiple times, so it's okay for me to run a lot of extra data to get better statistics. Does anybody do that?
Yeah, sorry, I can't do this. I was going to bring up the schedule. That is called parameterized query optimization. That's after spring break.
Gotcha.
So like he was asking, hey, can't you learn this shit? Yes. That's next class after spring break, after the proposals. Then your question of like parameterized optimization, that's later as well after spring break. Basically, what you end up doing is you have to start generating ranges because you don't know what these values are actually going to be. So you can't actually compute the selectivity. So you say, well, I'm going to assume like maybe the average case or like the lowest value, the smallest value. Different systems do different things. Postgres, I think, generates one. I think they choose the average value. You get the average value from the histogram, right? And then compute all this. This is independent of doing that parameterization stuff, right? In that case, like, but yeah, we'll cover the parameterization stuff later. And that's another example where the enterprise guys are going to be way more sophisticated than the open source ones for prepare statements. All right. Again, I don't want to jump ahead, but like this came up. It's like everything was going on here. And I think this is a good idea, but I guarantee you, like all the cloud vendors, Redshift, BigQuery, Azure, all those guys have tried this out on real data to see whether it makes sense. And then maybe they just don't talk about it. Yes.
What about the uniformity problem now? This is the independence, right?
Especially, all right. So this solves the independence problem. How do you handle the uniformity problem? So the response with that would be, if you assume that most of the times you're doing lookups on the heavy hitters, then you wouldn't go to the histogram buckets, right? You would go to the end bias histogram. So then, therefore, you would have an exact count, right? What's that? Scratches or sketches? Sketches. Yeah, I mean the count min sketch would help with that, right? But you don't have to do always.
If you have indexes, sometimes it will help if you want to spend time.
So statement is, if you have indexes, could you then probe the index?
Like you could store like aggregate information in a subtree, and then you know like the ranges of the subtree.
Statement is, you could store aggregate information in a subtree, and then you know ranges of values in subtrees, and you could use that to figure out. Yeah. There is nobody actually does this. There's a data structure called the history, which basically it's a B+ tree, but instead of key value nodes, it's basically histograms inside the nodes. So then you it's sort of like, as you said, it recursively tells you how big the ranges are as you go down. But as far as I know, nobody actually implements that in a real system. Okay. All right, so the next thing we got to deal with is join size estimation. And this is where things get really hard. And this is where it all falls apart. So it's given two tables, R and S. We want to figure out like what's the ranges of possible number of tuples we expect to emit, right? And for this, we're going to make a big assumption called the containment principle, where we're going to assume that every key that exists in one relation that we're joining with is going to exist in the outer relation, right? Assuming we're doing inner joins, right? And just trying to say again that the domain of the join keys that you're trying to join these two tables are going to overlap, right? Now, if you're doing a left outer join, that's a bit more tricky, but we can ignore that. It's basically saying like if I do a probe from a tuple in my inner table into my outer table, I'm going to find something, and then that just again you end up potentially overestimating the number of tuples going to match. But then there's other tricky things like, if an end-to-M join or the cardinality is not always 1-to-1, how do you estimate things? But we can ignore that. So the first big thing we got to do is align the histograms from the two tables we're trying to join on, right? Because again, since we're doing equidepth histograms, the bucket ranges are going to be completely different from table R and table S. So you take the histograms, do a quick processing pass on them to then just align what those ranges actually are. And that means moving things around. And again, now you can introduce some additional error because again, assuming uniformity within a bucket, say I'm moving the inner table to align with the outer table, as I start dividing things up and putting into the ranges of the buckets of the outer table, I'm going to end up with incorrect estimates again. Or again, if I have keys that don't exist and I start copying things over, then they'll have errors there. Then now, on a per bucket basis, you basically go through and figure out, okay, what's the number of tuples I expect to generate when I join my bucket from the outer table with a bucket from the inner table, right? And guys, now again, instead of saying, okay, what's the join predicate going to be across all the tuples, or sorry, all the values on the join key, if I'm looking on a bucket per bucket basis, even though it's been aggregated together, the scope is much smaller because there's only a portion of the table. Therefore, it reduces the effect of erroneous summarizations, erroneous errors. And then now, once I have the estimates on a per bucket basis, I just combine them all together, sum them all together, and then that produces the joint estimate for my entire for these two tables. So you do all those selectivity estimates that we talked about before. Again, well, assuming it's inner clause, so we know how to do that calculation to say how many matches I expect from one bucket to another bucket, and then you add them together, and that tells you what the estimate cardinality is going to be going above. So again, this is fraught with more errors because, like I said, as you divide the buckets up, the buckets are already coarse grained, and then now you're rebalancing the buckets so that the values align up, and that's just causing more problems. And then so now if your cardinality estimate for your join is inaccurate, what if you now join the output of your join with another table, another set of joins? Now you have this propagation, this error from one operator to the next, and that just makes just ruins the estimates all near the top of the tree. So it's a simple example here of just how bad estimations can go wrong, right? So we're trying to join three tables, A, B, and C, and we just have a predicate on the BID column here, right? So the way we would compute the cardinality for the entire query plan, right? Again, you would again, it's a top-down. If you're doing a top-down query optimizer, you would traverse down. You would have the memo table keep track of all this and keep track of what the cardinality is. But I'm just going to show you how you just do it from the bottom going to the top. So the first thing we're going to do is compute the cardinality of the base tables, right? So for A and C, that's simple because there's no predicate. So if I just know the number of tuples that are in both of those tables, then that's the cardinality estimate for them coming out. In the case of B, because I have the predicate on the ID field, well, that's again just computing the selectivity on the range predicate, which I showed how to do before. You base that on the histograms you would generate, and then multiply by the number of tuples you expect are in the table. But then now we come up to this first join here, and so now we sort of plug and chug this formula of, again, what's the total number of tuples either coming from, or we're taking the maximum number of tuples coming from A or B after the filter, and then assuming that I just match the two together, because I'm going to have for every key that's in A, it's going to match to something in B. So that's going to tell me that in this case here, I'm multiplying together because I can match with everything. And I divide that by the maximum number of tuples I expect to come up, and that's going to be a rough estimate of, again, how many tuples this join is going to produce. But then now I got to take the next join and take the output of what I just computed for this join and now feed that into the estimate for this join. So again, you see this effect where, like, if this thing has a bunch of errors in it, and then because I'm feeding it from up above, going inside this, and now this thing's got a bunch of errors in it, and I'm feeding that inside of this. So I have crappy calculations on top of crappy calculations, and then when I get near the top, my estimates are way off. And again, in the paper you guys read, they talk about how near the bottom, you might be okay with like scanning base tables, but once you go beyond like one join, then the cardinality estimates basically become all garbage. And we'll see this in a second. They're all going to underestimate the number of tools they expect to pick out. In a case of like Postgres, it ends up choosing the wrong physical operator for a join because it thinks not a lot of data is coming up into it, and then it runs it and gets surprised getting a ton. Yes.
This is not assuming independence, right? Because otherwise you would do a max of cell A AID equals BID times cell B dot ID greater than 100.
Like for this one here?
Yeah.
Yeah, so his statement is, I'm not assuming independence.
Right, because you're like the independence mistake is always that it says that the predicates are independently distributed.
So I'm trying to figure out what's the max number of tuples I expect to come up from this.
You don't want to match the joints. Like you're
The expected value, the max.
The max, yeah. So I gotta know, I think this many coming out, but then after I do that join, I'll have this many tuples coming out. Again, the main takeaway from this is that you start at the bottom, some of the assumptions we talked about before, they're gonna cause problems, but then as you go further up, the errors expand. So the paper you guys read, actually, this is the wrong citation. This is the original paper from 2015. The paper you guys read is the journal version, the expanded version, the better version of this paper, but it's the same core experiments. Some additional things. So this paper has been very influential in the database community. And it's not about how to build a cost model. At least the original paper was. This paper talks about alternatives to what other systems use. And instead, it's trying to show you, here's what happens when your cardinality estimates that your cost model is being based on are wrong. And in particular, they're going to look at joins. So the join order benchmark, this JOB thing, this is now sort of like a standard academic workload that everyone uses, but it originated from this paper from the Germans. And it's basically just showing you as you add, on a real data set, as you add more joins, what are the problems people have, or the systems actually have, right? So in the setup here, what they're going to do is they're going to load in the IMDb database, which I don't think is that big. It's like 800 megs or something. And then they're going to let all the systems run analyze, collect stats. And then they're going to get exact measurements of the runtime from the query plan. And then they want to see, again, as they introduce more queries, they want to compare what happens when they want to compare with what the true cardinality estimates are from the actual queries themselves, from what the database system's query optimizer thinks is the cardinality estimates. So it isn't about runtime, at least in this first graph here. It's just looking at the cardinality estimates to see how off are they. So again, this is a very famous graph here where they're looking at 5 different database systems. And the way to think about it is like this middle line here is when the cardinality estimate for a join operator in a query plan going up from 0 to 6 joins, whether it's above or below what the true cardinality estimate is. So if it's above this line, then it's overestimating the number of tuples an operator is going to generate. If it's below this line, it's underestimating it. Right? So the first one to point out is this guy here, this database system. So again, each of these blocks here is a different database system. This one is doing okay. Right? The overall trend is everybody's underestimating. The closer you are to the middle line, the better you are, right? So this one is doing much better than all the other ones. For these guys over here, they have sort of these clean step functions where things are progressively getting worse as you add more joins, which again, as we just showed an example before, if you assume that the errors are going to compound on top of each other as you're going up the query plan, so as I add more tables to join, and therefore more join operators in my query, right? If the input to my join operator is another join, and I underestimated how much data it's going to generate, that now feeds into my operator, and all I know that for that operator is whatever is being told coming down below me. So now I'm going to underestimate whatever the underestimated estimate coming up to me is, right? So again, that's why you see that sort of stepping function like this, right? This guy here is the worst, and it's a pretty big drop again, going from 3 tables to 6 tables here, right? All right, so if you've taken 721, you know the answers. Don't say the answers. For those who haven't taken 721, everybody know what database system this is? The paper tells you. Postgres. And what is the last one? Hyper, right? So that's before Umbra. There was Hyper, right? It's the system from the Germans. All right, let me take a guess what the best one is. SQL Server. Okay. And what about the worst? Oracle. Yeah. And then DB2 is the last one, right? All right, so what's going on? Why is SQL Server so good? Right? Well, he just poo-pooed that exponential backoff on the selectivity estimates. But that's I'm not saying that I would attribute all of that to this, but that's exactly what that exponential backoff is trying to solve.
Yeah.
Where you're not underestimating as you go up the tree, right?
It's just putting an upper bound on how bad you can be. That's what it's really.
No, it's trying to like yes, but like you need that upper bound to be higher.
His statement is that exponential backoff is a way to get upper bound on how bad you actually are.
Yeah.
Yes. Again, I don't think I don't think they were sitting around like, hey, let's try this. Like they randomly thought about it, right?
They didn't want to look like the third graph. I understand that the idea is not to be really, really bad, and hence it makes sense.
I mean, these experiments are run. Actually, SQL Server 20. Actually, if this paper is 2015, SQL Server 2014 had that exponential backoff. I actually don't know whether this is actually running it then. Maybe wrong. I'll double check. All right, but so the paper talks about what SQL Server is actually doing is it's actually a combination of histograms and sampling, right? Hyper does sampling, but I don't know whether they did it for this earlier version of the system. It added later on. There's other things too. I think they match on strings, and I think SQL Server maintains separate tries to do that and get more accurate estimations, right? But again, like in my opinion, if you take the textbook, like take the database textbook from the intro class and go look up how to do cardinality estimations and assume you're doing the independence clause and uniformity of the values in a bucket, like you'll end up with exactly the step function in Postgres, because Postgres basically implements the textbook definition of how to do cardinality estimations. Yes?
I see those figures are quite symmetrical. Can we just add can we calibrate them with a constant adjustment?
So his statement is, hey, look, in case of Postgres, for this workload, it's almost a constant factor off, right? We're log scale, but yeah. Like, can't you just fudge it and push it up? Yeah. So, going back to what I was saying before, like Microsoft didn't just decide to do the exponential backoff on a whim, right? That they looked at probably real customer data sets and workloads, which they have access to, because if you're paying Microsoft for $100 million for your SQL Server licenses, because that's the core of what your business is running on, like major banks run on that, then like if you can make things better, could you turn over some data to SQL Server so they can look at it, they'll have access to that. Now the cloud vendors have everything, right? So they can do a bunch of experiments, I know. But like to answer his question, like, yes, if you had a way to instrument your data system to identify that you see this underestimation pattern over and over again, could you introduce that fudge factor? Sure. Would it work? I don't know. Right? It depends on the workload.
Yes. And Redshift said anything about as to what they do?
In terms of how they do.
They handle the independence and how they handle.
The question is, do other cloud vendors like Redshift?
Because the cloud vendor, I feel like it would be slightly different in how they approach it.
His statement is the cloud vendor would be slightly different in how they approach it in terms of like what experiments they would run.
No, because they have so much data and because they can sort of calibrate it a little better. His
statement is that a cloud vendor would have so much data and therefore they can have a better calibration than like, again, the SQL Server team probably has a lot of workloads, but definitely not at the scale as a cloud vendor. But of course, they run SQL Server in the cloud now, right? So I don't know what SQL Server does. They collect telemetry on everything. So whether or not within a single query plan, are they collecting what the cardinality estimation is for a query plan, and then when they run it, what the true cardinality estimation would actually be? I don't know. But one can imagine they do, but who knows what they're actually doing, right? it's not a really sexy part of building a database system, right? Again, the challenge is that, again, if you going back to the lakehouse thing, like if you have no stats at all, then the fudge factor might actually not even make any sense, because now like, what are you actually estimating your estimates based on, right? Again, this is a different model than the cloud systems like Snowflake and others. Well, Snowflake has managed storage, but like if you're like Redshift that's running off S3 or Databricks running off S3, like, you're not going to be able to build a sample. You have a bunch of Parquet files that you may have never seen before. So maybe as you start scanning those Parquet files, you can build some kind of sample, hoping that you're going to maybe read them again. But that's additional cost to the cloud vendor, which they actually might not want to eat, because if they generate a crappy query plan for you, you're paying for it, not them, right? Because you pay for compute time, right? So it's this perverse thing where like, it's not really in their interest to make your queries run really fast, because if you're paying for, you're paying for the wall clock time of the CPU, then like whatever. But of course, then now if your queries are crappy, then like there's competition from other vendors. Like it's a very crowded marketplace. I get these companies they're billion-dollar companies. I guarantee they've looked at something, and whether or not they publish it, I don't know. Sorry, I know they don't publish it. At least I haven't seen it. The Microsoft one is the only one I know that talks about it. Because again, everyone builds the first time they take the textbook, right? They just do all the formulas that I showed you here. All right, so I want to show one example with Postgres. Again, this is an older version of Postgres 9.4. I think the latest version is 17 now. But I want to show how the problems that you have when you have bad estimates. But then if you can inject the correct estimates in, then you end up getting better query plans. So on the y-axis here, this is the percentage, how much slower the query is. This is the percentage of the queries that are fit in this bucket, and then down here is the scale magnitude of the performance difference between like the best plan you could have when you have the true cardinality estimates, right? So when I think about this is like, for this chunk here, 60% of the queries are slower than the queries you would generate if you have accurate cardinality estimates. And again, because Postgres is underestimating after join after join, right? So the problem is that because Postgres is underestimating the joins, just going back here, right? As I add more tables, right? When I start doing above 6 joins, it's thinking like I have a small trickle of tuples coming up from my join operator from down below. So it ends up doing things like, oh, well, it's not a lot of data. I don't need to build a hash table to do a hash join because it's like 5 tuples. So let me just go ahead and do a nested loop join, right? And then, of course, now 100,000 tuples show up, and now you're doing a nested loop join, and you're screwed, right? So if they go back and they force the query optimizer to never choose nested loop join, they allow for an index nested loop join, because in those cases, if you have an index, it makes sense. But if you only make it allow to do hash join or cert merge join, right? Now you see that you're getting more queries are going this direction, where you're getting closer to the optimal performance you would get, right? And then this is an early version of Postgres 9.4. In 9.6, if I remember correctly, Postgres had the ability to rehash rebuild the hash table without crashing the query, from restarting from scratch all over again, right? So again, this is problematic if you underestimate the amount of data you're going to generate, because if now if I'm underestimating the number of tuples that are coming up, I said, okay, I have 1,000 tuples coming up. I'm going to do a hash join. So let me build my hash table that can accommodate 2,000 tuples. 100,000 tuples now show up. What do? Right? And so they added the ability Postgres added the ability to recognize that I have more tuples coming up to me than I expected, and therefore let me go ahead and just rebuild the hash table. So if you add this optimization back, they backported it to Postgres 9.4, right? Then that reduces some of the error as well, right? And made things run faster. All right, again, the takeaway here again is that, well, it's the next slide, like that if you can generate better query plans because you have better cardinality estimation, then in sometimes that's actually going to be much better than designing your system to be super high performance and having all these additional capabilities and additional features. Now, Postgres is a 1980s architecture. It's not meant to do OLAP, but people still do it. And so again, if you have crappy query plans, then whether it's a row store or a column store, it's still going to be a terrible system, right? They show that cardinality estimates are routinely wrong. And so to the extent you can design your system not to rely on the estimates or be able to adapt the query plan while it's running, which we'll cover after spring break, then that's better than trying to, and that might be a better target for your engineering time to modify the system rather than trying to make a more complex query cost model, which is sort of what they say here, right? That if you, or down here, like instead of spending time having super accurate statistics and super accurate cost model that try to account for everything that your data system is going to be doing, like remember we talked about like in DB2, they have a bunch of these little micro benchmarks that run, or in small base, they try to aggregate together all these low-level operands you're going to execute when you run queries. Instead of spending your time making this very sophisticated cost model, if you just made your cardinality estimations much better, then you'll get a lot of the benefit. Well, you have a bigger benefit in the system. Yes?
There was another lesson, right? Like, which was if you account for errors within your estimate, like you could go with an approach saying that, hey, my cost isn't 1,000, my cost is 1,000 plus or minus 500,
yes,
plus or minus 200, and you then use a heuristic to ensure that you're picking the half joint over the nested loop joint. What do you think of that idea?
So statement is that's when this one is, right?
It's aligned with the second point, right?
Yeah. So statement is like if you have a mechanism that can get triggered in your query optimizer where you have a way to say, I think I'm going to be wrong within some bounds, and have that be part of the decision making when you decide what physical operator to use, right. Or even within the physical operator to like allocate memory or something for the operator, right? I think that's a good idea. The challenge of that one though is I think that could end up being like a lot of patchwork code, like throughout the optimizer. If I think this, then do that, right? Whereas again, I think I 100% agree with Victor here. Like you should make this be as good as possible before doing anything else. Now, whether or not you're using machine learning to fix that, or the fudge factor he mentioned, right? We'll cover that later. But making cardinality estimation, getting that to be as good as possible, that has cascading benefits throughout the rest of the optimizer.
I mean, but like as you said, the best guys that we know are still using square root solution, right? To fix this.
And you really hung up on that. It's like,
no, it's just to me the idea that you take on the estimate, like you consider the bounds, and then you do the if else when you have like when you consider when you ask for a cost model, hey, what is the cost of this thing? It says the cost is 1,000, but I might be off plus minus 500. Knowing that information and then setting up rules so that, hey, I'm converting a logical join to a hash join or a nested loop join, depends on whether or not, you know.
all right, that's different. All right, so whether or not you have like heuristics or anything else within the optimizer about making certain decisions, like when I'm choosing a physical operator, like having trigger mechanisms like that are hard coded for certain things, that's one thing. What you're proposing is instead of passing around a single number as the cost, as the cardinality estimate, what if you pass around a range, maybe like a confidence interval, right? Yeah, or standard deviation, and then have that be part of your calculations.
The minimum robust.
All right, so there is research on what's called robust query optimization, where like you can't guarantee that it's going to be optimal, but like it doesn't always end up with the worst plan, right? The average does great.
It's not that bad. It's like another.
It's called robust query optimization. We're not reading any papers on that, but I can share some afterwards, right?
And you think that is a good idea?
Do I think robust query optimization is a good idea? I mean, yes. I don't. Again, I'm not an expert in this. I haven't seen. Nobody implements it. I was on a thesis committee for somebody in Germany who was doing this. there again, the results look promising. Again, if the workload is noisy, the data is noisy, and like the hardware you're running on is also maybe unstable because like noisy neighbors and things like that, then it probably makes sense. But again, no commercial systems as far as I know implement it. Snowflake would say rather than adding all the sophistication to the query optimizer, BigQuery would say the same thing. Like just have the runtime engine be adaptive. So no matter what crappy query plan you get, as you see the data, you can adjust things. Which is not, and we're not talking about in this class, but they would argue that's the better way to approach this. Okay. All right, so I want to finish off. We're talking about two implementations, Postgres and SQL Server. So the way Postgres works is that the operating cost that it computes is basically a weighted sum of the number of pages they expect to access to do some operation, run an operator, plus an estimate on the number of tuples they expect to access in memory. And remember last class I talked about how, or showed the example where there's these weights you set to say what's the relative cost of like random I/O to disk I/O to doing some amount of work in the CPU, and it requires somebody, a human or a database provider or machine learning algorithm, to figure out how to set those relative costs in order to figure out how to make this all work. So the Germans said that when they looked at the Postgres code, that it's actually quite complicated. Postgres is almost 40 years old now, and that the cost model is a very sophisticated, complex piece of a bunch of code. So they had a question of like, okay, well, if you replace this complex default Postgres optimizer with a really simple one that just says, here's the number of tuples I expect to come up from an operator, is that going to do better or worse for query plans? So this now is going to be the actual runtime of queries. So lower is going to be better. So along this column here, this is going to be, if you rely on Postgres, like analyze to generate the statistics for its cost model. And this column here would be if you inject the true cardinalities, so this is one of the students, or one of the groups in this class I'm working on, into Postgres, what happens there. And then the rows are, if you don't tune those knobs I mentioned for the relative weights for like CPU versus random I/O and sequential I/O, here's what you get. The middle is if you actually do tune them correctly. And then the bottom one here is the cost model. If you don't, the simple one, you just estimate the number of tuples that expect an operator to spit out, right? And you can kind of see that the overall trend is this one does pretty well, right? If you have true cardinality, they're all about the same. But assuming you're not going to have true cardinality, as we know that's the case, then the overall the scatter down here is much tighter than the others, and the runtime cost is lower. So again, this is empirical evidence for them saying like, all right, you can try to make a real sophisticated cost model, but at the end of the day, it comes down to make sure your cardinality estimates are super important. And if you go look at the Postgres code for the query optimizer, I know it's hard to read, but like you kind of see here again, here's all the things that they're accounting for in the cost: sequential page cost, random cost, CPU tuple, index tuple, CPU operator cost, and then parallel setup and processing cost. I was actually surprised to see that there was very few magic constants in this code. There's only one here, where for the append the CPU cost multiplier. So this says append and merge append nodes are less expensive than some other operations which use CPU tuple cost. Instead of adding a separate GUC, which I forget what that stands for, estimate the per tuple cost as a CPU tuple cost multiplied by this value. So you just some magic constant they set to 0.5, and they multiply some costs like this when you're running these different operators, right? But everything else is being computed from the cardinality estimates and that are then weighted by the flags you can set in the configuration file. All right, SQL Server, we already talked a lot before. So I want to talk about, in addition to the exponential backoff, two other things that they do is that the cost calculation for an operator is not just the number of, is based on the number of tuples I expect to spit out, the cost of generating all the tuples as part of my output. They also keep track separately of the cost of producing the first tuple of an operator. And the idea here is that if you want to say, is a nested loop join going to be better than an index nested loop join? Well, for a nested loop join, there's no real cost setting up the on the inner table to do the scan on it. I jump my iterator to begin the table and I produce the first tuple. Whereas if I do an index nest loop join, there's a cost of probing that index, right? Finding whatever the leaf node, then jumping to the tuple, jumping to the page that has the tuple that I want, and those costs aren't the same. So even though again logically both the index nest loop join and the nest loop join are producing the same number of tuples, the cost of actually getting them is slightly different. There's other things they do to keep track of, like if I know that I'm going to see the same value over and over again on the inner side, or in the inner relation, then I don't have to go do a probe in the index to go find the thing I'm looking for. I just use the cache result. The operator keeps track of the last thing that it produced, and it sees the same thing, it spits that out again. So there's other tricks like that they do to try to be more fine grained in their estimations. Another thing they do is maintain what they call roll goals, where it's not really a physical property or property of a query plan like we talked about before. It's like this high level thing that they maintain for a query plan that just says, at some point in the tree, here's the number of tuples that I'm going to need, right? And the idea is that when I start doing calculations or doing cost estimates for different operators at lower parts of the tree, if I know I only need one tuple, like I have a top k, like give me the first key, the first value for some relation below me, like think of like a limit clause. If I only need one tuple, then choosing to do maybe like an index probe would be better because I only have to probe that index once. Whereas if I need to get all the tuples, because it's like a limit 10,000 or something, then maybe a sequential scan is actually better. So this is basically saying that the choice of what is the best physical operator down below me in the tree can depend on what is actually going to be consuming my output above me. And so this roll goal is basically a global thing. Again, I don't know if it's global or it's within the subtree, to keep track of like how much data I need coming up, and that can help me refine my cost estimates down below. And then we've talked about the exponential backoff that he hates, but just trust. Okay, so let's finish up. As I said, cardinality estimations is the hardest part of building a query optimizer. Again, the paper you guys read talks about a lot of the trade-offs and different approaches to this. And it's not one thing like, oh, if you have better histograms, that's going to make a difference. I think it's the combination of having good histograms, the right cost, sort of cardinality estimation formulas, additional data structures to get cardinality estimates for substring matching, like a trie or something. Or in the case of Hyper, they use samples or this. So again, it's the combination of all the techniques that we've talked about so far that can end up producing, help you produce better results. Of course, the challenge is that when people build these optimizers, oftentimes they hard code a bunch of crap in there, and then no one ever goes back and looks at it again. So like I showed that 0.5 in Postgres. I didn't run blame on it, but that's probably written years ago, and no one ever has gone back and say, does that constant value actually don't make sense anymore, right? So as I said, the German research shows that the cardinality estimation is more important than sophisticated cost models, and all this seems like it'd be amenable to machine learning. This is why we'll cover learn methods or learn approaches, cardinality estimations after spring break. Again, I don't want to think I'm just picking on SQL Server about in Postgres about their hard-coded value. This guy here sent me an email. Ignore that. Sorry. Whatever. He sent me a link here because he was looking at DocumentDB. So DocumentDB is a front end that Microsoft released and made open source that speaks the MongoDB wire protocol, and so it basically allows you to treat Postgres as if it was MongoDB and store JSON in there. But then he pointed me here. If you go look at their cardinality estimations from their predicates for the BSON operator selectivity, right? It returns 0.01, right? And it says the dumbest possible notation, assume 1% rows are returned. Again, that's sitting there in the code. People are running this in production, right? And again, I didn't run blame, but I think it was at least a month ago when this was released, right? So again, I'm not picking on Microsoft, not picking on DocumentDB here. Like you see this crap all the time in when people build query optimizers, because again, it's hard. You're trying to build the thing. At some point, you have to start making assumptions, and someone picked 0.01 for this, right? Again, you're just making guesses on top of guesses, and there's the original guesses you're guessing based upon could be just like this, which is terrible. All right, so again, that's it for today. Next class, again, the Monday after spring break, everyone has to give a 5-minute presentation on the project proposal. And around, if you want to discuss your plans for this, or you want to send me the slides and want feedback, I'm happy to do that. And then we'll pick up again on learn cardinality estimation on the Wednesday after spring break. Okay?
We're gonna go with that brown. Matter of fact, hold the cup. This is like that wood grain type of shit. Shout out to Blockhouse, my dogs. Catch one, Big Al, Mike Stroke, Gumbay, all Dynamites. I'm not the one who be amping up the weak ass rhymes. If you to spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like I make them hoes fuck quick and suck dick. Crown me as a thug from the gutter. Shit, some niggas claiming that the rapping is sudden. Don't push the button, yes you motherfuckers are frontin', you don't.